So first of all, next Monday, we have another class at 4 p.m. And exam will be 6th November. I don't know the time, what time, but it's on 6th. Most likely it will be in the afternoon again because so one of your colleagues is in Peru and his time difference is -7 hours. So most likely it will be in the afternoon. But I don't know the precise time. But this I forgot to check. And the exam, okay, again, I don't know. I don't have any experience, with the exam through the Zoom and things like that. So I don't know exactly, but I think it will be written exam. Written exam. Written. Okay, so any questions from the last time we started reading the the concepts of positive roots, negative roots, and the simple roots. Right? So it was exactly like what we were doing in HEP-3, right? But now it's in a completely general way. That is what we do. Now, there was one chapter which I didn't do, that was chapter 13. So no. So chapter 13, basically what it in chapter 13. So what I would suggest if you have not looked at it, to go through it this week. And so that on Monday, if there are any questions on that, we can discuss that. If you find it difficult when you go through it during the weekend, then I can do it on Monday. Spend time on that. If you have already done it, then I can spend Monday on something else. For example, the spinor representations of SO groups. So depends on how it's not difficult. Actually, in fact, I noticed that most of the things are exercises there. Most of the things are exercises in this chapter 13. It is straightforward. There are no complicated concepts involved in that. It is a straightforward calculation. But they are important to relate to what I'm doing now. I mean, in this chapter, the 14th chapter. Okay, so let's continue with this. So we proved everything, right? Given a positive root alpha delta plus of level n. What was that? No, we didn't go to that Karpman matrix, right? So we went up to this theorem 14.1. Right? We went up to 14.1. Any questions on that? On the 14.1? I mean, just write the statements. So the theorem 14.1. One statement was that if alpha I and alpha j belong to the simple roots, belong to the set of simple roots. These are simple roots. They were the notation. Simple roots. Then the statement was that alpha I minus alpha j, it does not belong to delta. So it was again, I mean, exactly like what we had in for SU3 case. SU3 case, we had alpha 1, alpha 2. These were the simple roots. If you take alpha 2 minus alpha 1, this was not a root. No? And same thing if I take alpha 1 minus alpha 2. I mean, alpha 2 minus alpha 1 would have been here somewhere, right? So this was the direction alpha 2, alpha 1. So if you go back, minus alpha 1, but that was not part of SU3. SU3 roots were this, no? Alpha 3 and the minus alpha 1, minus alpha 3, and minus alpha 2. So this were the 6 roots. of which where we chose the positive roots to be everything on the other side and negative roots to be everything on this side, and with simple roots for this. Simple roots for this. So this was not there. And this was proof. We could give a proof of that. It was a reason, quite a simple proof. Then the other thing was alpha I, alpha j is less than or equal to 0 for I not equal to j. For I equal to j, of course, it's going to be positive, right? Because alpha I, we already showed that the metric was positive, right? So that could be positive. But the point here is for I not equal to j. So again, these are in the same sigma. And that proof was basically coming from this quantity, which plays a very important role throughout, 2 alpha I, alpha j, divided by alpha I, alpha I. Okay. This was P minus Q, right? It's P minus Q. So what was this P and Q? It was starting from alpha j. You're looking at starting from alpha j root. We are looking at the alpha I string through it. No? So alpha I string through that. So it will be alpha j plus alpha I, alpha j minus alpha I, etc. So we have this string, and this string. So this goes up to alpha j minus p alpha I. It goes all the way up there. And there it goes all the way up to alpha j plus q alpha I. Now the point is that if this is simple root, then of course this doesn't exist from the previous theorem. That the difference, if I take alpha j minus alpha I or alpha I minus alpha j, it does not exist. So this root is not there anymore. So all of this part is not there. So p is 0. So this means p is 0. So it can only be less than or equal to 0 because q is some non-negative integer. No? So for this reason, it's less than or equal to 0. If it is equal to 0, okay, then there is some also we will see. So if q happens to be 0, that means there is nothing, not even that exists. No. So it's just alpha j. So neither alpha j plus I exists, nor alpha j minus I alpha j minus alpha I exists. And that means that if I look at the commutator of x alpha j, x alpha I, you see this should have been some x alpha I plus alpha j. But if this root doesn't exist, then this means it is 0. No? If you are saying that if q is also 0, okay, then this also doesn't exist. This root also doesn't exist. No? So then you are just a solitary guy here, alpha j sitting here. There is no string at all. And that would mean that since this root doesn't exist, this commutator is 0. So that is the thing here. Okay, this we could have concluded. I mean, this was not in general true. If we are not talking about the simple roots, it was just arbitrary roots here. No? In that case, even if you find this to be 0, you have no guarantee. Maybe it is 0 just because p is equal to q. No? In that case, you cannot make any conclusion. But in this particular case where these are simple roots, we know that p is 0 anyway to begin with. P is 0. Okay. So if I find this result to be 0, then q has to be 0. So that's it. Okay, and then the third point was that, well, actually we went through other way. We first proved the fourth point. Fourth point was that if alpha belongs to delta plus, then I can always express alpha as some integers. Okay, here it's written C, but it doesn't matter. Ni alpha I, some lower, where Ni are all non-negative integers. That was the statement, and that statement was simply because by definition, I mean, if alpha is not a simple root, I should be able to write alpha as some beta plus gamma, where beta and gamma are positive roots, right? Then you go back to ask, is beta a simple root or not? If beta is simple root, you leave it there. What about gamma? Is it a simple root or not? If it is not, then it should be again sum of two positive roots, right? So this way you keep going. And the point is that why this keeps going is that, which I didn't mention very much, because remember, all of this discussion came, we said that there is some regular element in the kappa. I don't remember what we were calling. I think we were calling H0. H0 was a regular element, right? Which had such that none of this alpha H0 was not equal to 0 for all alpha belonging to delta. That was a regular element. So this is the same as what we discussed a long time back. I mean, not long time, maybe 1 week back. That we said that the regular element of the kappa was an element which has a minimum number of zero values. And this tells you that since this is not zero for any alpha, none of the roots have zero eigenvalue with respect to H0. No? Of course, the kappa H0 will commute with every other kappa. So it will have zero modes, but that zero mode will be equal to number of zero modes will be equal to the number of zero eigenvalues will be equal to the rank of the dimension of the kappa. But no non-zero root is a zero has zero eigenvalue. That is what it means, right? Because I mean, what does it mean? This means H. Well, in general, some H with the X alpha was equal to alpha H X alpha. Right? This was the eigenvalue. No? But now we are saying that for H0, we have this alpha H0, but none of this alpha H0 is zero. So that's the point. So it doesn't have those eigenvalues. So it's a regular element. Right? But now if it's a regular element, and then how did we define the positive roots? We said all those alphas, alpha H0, which are positive. So all those alphas, so alpha belongs to delta plus if alpha H0 is greater than 0. And if it's the negative roots, it is negative. So that's one. Now imagine that I started with something. So now I started with some alphas. Okay. Now this is not a positive root. Alpha belongs to delta plus. Now suppose it is not a simple root. Then we are saying that by definition of this, alpha must be equal to some beta plus gamma, right? Where beta and gamma are, so if alpha does not belong to the sigma, then alpha, I should be able to express alpha as a sum of two positive roots, where beta and gamma both are positive roots, belong to positive roots. But now if you look at alpha of H, H0, then will be equal to beta of H0 plus gamma of H0. So notice that the values of beta H0 and gamma H0 is less than alpha H0. Because both are, everything is positive. Sum of two positive terms, and this is some positive term. Okay. So each of these guys will be less than that. Okay. At the next step now, let's say, suppose that both of them are not simple roots. Then I should be able to write beta as some something, let's say delta plus rho, and gamma equal to something, say epsilon plus something else, I don't know, rho prime, let's say. And then when you evaluate these guys at H0, the values of these two guys will be less than that, which means they're all going to be less than that. So it keeps decreasing. You see, as you go to the next steps, the values will keep decreasing. So you're not going to get a situation where at some point in this thing, again, you get back, when you look at the linear combinations of these, again, somehow alpha appears there. No? You'll not go back, you'll keep coming down. At some point, and because of the finite dimensional system, I mean, there are only a finite number of roots. At some point, you have nothing left over apart from simple roots. So you should, at the end, you'll arrive at just sum of simple roots. Each one of them can be expressed in terms of sum of simple roots with integer coefficients. There's no order there. The H0 is providing you an order. So we are coming closer and closer to the line of 0. The line where the H naught is 0, alpha H naught is 0. But once you have proven that every such thing can be expressed as so alpha can be expressed as some ni alpha i's. Alpha i's are in the so this belongs to sigma, where these are non-negative integers. So this is the point. But once you have done that, then the third theorem is automatic. The third statement was that alpha, the simple roots provide a basis. This is because we already know that the full set of alphas provide a basis. Right? So it spans, which means the full set of alphas span the H star, the dual vector space. Right? But since every alpha can be expressed as some linear combination of sigma I of the elements of sigma, okay. Therefore, the sigma spans there. Okay. Now let's go to the yeah. So essentially, now the very important thing is that basically you can characterize each D algebra by just specifying some minimal set of data. And that minimal set of data is what is called the Cartan matrix. The minimal set of information which uniquely fixes the algebra. So, and that is the so-called Cartan matrix element. It's called Cartan matrix. This is a matrix which is rank times rank. R cross R is a rank. This matrix is an R by R matrix. And its entries are, if I look at the Aij, so I and J are between 1 and R. Okay. This is nothing else but 2 alpha I, alpha J, divided by alpha J, alpha J. Well, this is the same as what we were calling all this time. We were calling this N, alpha J, alpha R, no, what were N alpha J alpha. So this is the thing with if you look at the ith alpha I root and look at the alpha J string passing through it, then this is a number which was a P minus 2, the corresponding P minus 2. So it means the lowest one is alpha I minus P times alpha J, and the highest one is alpha I plus Q times alpha J. Unfortunately, I mean, this for some reason, like, yeah, I mean, for some reason they just use this convention. I mean, it's not big deal. It's kind of a reversing, but it doesn't matter. I mean, that has same. So once you give this, once you specify this data, right? So this R by R matrix, then I mean, these are all going to be some integers, right? I mean, so with the structure is very clear. What the structure is going to be. Look at the diagonal first diagonal elements. If I look at I equal to J, that's all 2. If J equal to I, all this cancels, and there's just 2. So diagonal elements are trivial, they are all 2. So that doesn't carry any information. The information is carried by the off-diagonal terms. And the off-diagonal terms, again, we know these numbers can only be -1, -2, or -3, right? Why minus? Because this is P minus Q, and we know that since these are simple roots, P is always 0. I mean, that's what we discussed before already. Right? So this is going to be some non-negative integers, or 0. 0, -1, -2, or -3. These are all only possibilities. And so, for example, on the other hand, we also know that you remember the table which we discussed before. The table, the only possibilities were if I take any roots alpha beta and look at I mean, not necessarily, this is completely general. It's not just for not just true for simple roots. Any root. The statement, the table, this was the table 14.1. So there the only possibilities were, if I look at it, so n alpha beta. So we know that n alpha beta and beta alpha is 4 cos square theta, where theta is the angle between alpha and beta. So let's call it theta alpha beta. This is what we found. So because when you take the product, the product is simply 4 alpha beta over alpha alpha and beta beta. I mean the square and beta beta. So that's why this becomes that. See, the length cancels. No, length of alpha length of alpha square cancels with this length of alpha square. Length of beta square cancels with that. So what is left over is 4 cos square theta alpha beta. And then we say that this can only be, on the other hand, we know this is integers. So this has to be integers, but bounded by 4. No, because cos is always less than or equal to, cos square is always less than or equal to 1. So the only possibilities were 0, 1, 2, 3, and 4. But 4 was trivial because 4 was just saying that alpha and beta are parallel. No, because theta, if it is 4, then theta equal to either 0 or pi. So alpha and beta are parallel. So either alpha equal to beta or alpha equal to minus beta. No, the 0 degrees or 180 degrees. So this is trivial because then we are not talking about two different roots. We're talking about the same root essentially. So if they are distinct root and not negative of each other, then the only possibilities were this. And but then you see these are all prime numbers, no? So the only way is that, so for example, if it is 3, if the product is 3, then one of them must be 3, other must be 1. No, there's not a non-prime factor here. If, for example, the 4 was there, then you could have 2, 2, 4, 1, and so on. No? But these are all prime numbers. So one of them will be 3, other will be 1. Similarly, if it is 2, one of them will be 2, other will be 1, and so on. So that means that if suppose this number happened to be 3, then let's say this number, say alpha for the 1, 2, suppose this one happened to be minus 3. Then this is going to be minus 1. Because the product of these two numbers, I mean aij times aji, is exactly that number that we're computing, right? So it'll be that. Or suppose, for example, something here says minus 2, then this will be minus 1. Or other way around. This could be minus 3, that could be minus 1. Or if it is 0, is 0. 0 means, okay, nothing. Or it could be minus 1. For example, you could have a situation where minus 1, that's the for the 1. So basically what will happen is that this kartan, the off diagonal terms will be one of these numbers, minus 1, minus 2, minus 3. And it's wherever you see a minus 2, minus 3, etc., if you look at the transpose element, if you look at the other element, will be minus 1. So this is the structure. But it's just this information. This information is basically capturing this information. That's what one is doing, right? This off diagonal, the data of the off diagonal terms here is contained in this information. So basically it's just this information. This information is enough. Why? Because it tells you the length of the chain. We know once you tell me this number immediately tells you, for example, suppose this number was 3, minus 3. Okay. Then this would say that I should go from alpha j to alpha, this is alpha j string. Sorry, this is alpha j string. So I start from alpha I go to alpha I plus alpha j, then alpha I plus 2 alpha j plus, and then alpha I plus 3 alpha j. So I know this is the string. So this will be a 4-dimensional representation with respect to the SU2 defined by alpha j. So that's the way it looks. Okay, so now what I will do is I will take some simple examples. Maybe, okay. For me, I mean, looking at this matrix is not, does not give you, you like to see a picture. When you see a picture, it's much easier to remember in the mind. When you look at these numbers, okay, random numbers or what, It doesn't tell you much. So there is a pictorial way of representing this, a purely pictorial way. And the idea is that, this is called Dinkin diagram. But the information is the same. What the information the Dinkin diagram contains is the same information this Karpman matrix contains. It is just that it's easy to see it in the brain when you have a picture. Okay, so the rules are for Dinkin diagrams. So the rule is that for every simple root, you put a dot, put a small circle, let's say. A small circle, or a dot, doesn't matter, small circle, or a dot. Okay. So for example, let's say, the number of these circles will be exactly equal to the rank, right? Because the number of simple roots is equal to the rank of the algebra. Rank being the dimension of the Karpman algebra. So if R is the rank, then there will be R circles, small circles. Okay, whatever. Now what you do is that this number that you found, 0, so the possibilities were 0, 1, 2, and 3, right? So let's say Aij times Aji can be 0, 1, 2, or 3. Or even directly Aij can be 0, minus 1, minus 2, minus 3, right? So what you do, so let's say this is the ith dot. So this represents alpha I. So this represents alpha j. So each of these dots are representing some simple root. So suppose, for example, Aij, suppose this was 0. Okay, then these two things are not connected. You don't connect them. Okay, but if it is say minus 1, then you connect it with one line. So this is Aij equal to minus 1. On the other hand, suppose I have another one, let's say some alpha k and alpha L. Okay, and maybe for that the AKL happens to be minus 2. Okay, in that case you connect it with two lines, and so on. So this number of lines you connect it with is equal to this modulus 1, 2, or 3, or 0. So the maximum would be a 3. Maximum would be this 3. So that would correspond to Aij equal to minus 3. That's the okay. So this is the way you draw. So this basically captures all the information, because the only relevant information was that this information, this off diagonal, because diagonal is always true. Okay. But on the other hand, we also saw in the same table that there's one more information which one has to give, because in that same table we saw that if let's say Aij, if A alpha, so what we're calling N alpha beta, say is 3 or minus 3, and N beta alpha is minus 1, then you know from just by looking at this formula, one of them involves, so let me just use the A since I'm doing the A. So Aij is minus 3 and Aji is minus 1. Okay, then we know that here, if you now take the ratio of these two, Aij divided by Aji, then this cancels. Okay, and then you just get the ratio of the length square of alpha I and alpha j. No? So this ratio will tell you that the length square of one of these roots is 3 times the length square of the other root. Right? They're not the same length. Okay. So in that case, so for example, if I look at Aij divided by Aji, then I'm going to get, this will be alpha I divided by alpha j. So you need to also give it this information of these two, for example. Say, let's say this is, so let's say this is Aij equal to -3. So I have 3 lines. Okay. But I need to also specify which one is the longer one. You see, one of them will be longer than the other one. No? So if this is now, for example, so Aij is -3 and Abi is -1, so this is equal to 3 in this particular example. That means alpha I is bigger than alpha j. It is enough to specify which one is bigger, because I know once I have 3 here, 3 lines, then I know this is going to be 3. Right? So length of alpha I will be square root of 3 times the length of alpha j. Right? So it is enough to say which one is bigger or which one is smaller. No? So the okay, in the notes, in this lecture notes, the rule was that the shorter one, you fill it up, the shorter one, make it a solid dot. But I don't like it because, I mean, first of all, it's very time consuming to fill up the dot, you know. But also then you keep forgetting which one is supposed to be the smaller one, the one with filled up or the one which is not filled up. No, I keep getting confused. So I think the best thing is, so the rule, which I like it better, is that you make an arrow from shorter to the longer one. Okay. So this arrow is telling you that as you go this way, this one is longer than that. Okay. That is an arrow. So this arrow convention. So this arrow means the length of alpha j is less than the length of alpha I. So this is it. So all this information, this entire information, you can just give it in a simple picture. And by looking at the picture, you know immediately what are the. When you have a single line, so suppose I have a single line, then of course I don't have to specify this, because when it's a single line, that means both Aij and Abi are at -1. So the ratio is 1. So in that case, the lengths are equal. So you don't have to, you don't need to, I mean, there's no arrow because both are equal length. Okay. But whenever you have 2 lines or 3 lines, one of them will be bigger than the other one. So you just specify, for example, if alpha k is bigger than alpha L, then you put it like this. So if length of alpha k is root 2 times length of alpha L, it's going to be root 2, because then you see the ratio will be then 2. If the number was 2 for the 2 lines. Okay, so this is a notation, I mean, simple notation. Okay, 2 things I want to specify, say that. So in general, if I have some picture like this, some dots like this, now there can be all sorts of connections, right? I mean, every time this Aij, I mean, so for example, let's suppose this is I, this is J. Now you ask the question, what about the J and K? Again, what is the AJK? From AJK, again, it could be whatever it is. Maybe it could be 2 lines or something like that, or it could be 3, depending on the particular algebra you're looking at. No? Or it could be, for example, this may be connected to that. Right? Maybe there is a single line connecting that. So AIL may be equal to -1. It may be equal to -1. In that case, I have a line like that. Right? So you have this R dots sitting there, and just look at each pair and decide what your numbers are, how many lines you have to put, and then if the number of lines is more than 1, then you have to also indicate the arrow. That gives you the complete information about it. Okay, so that's a Lincoln diagram. Okay, so now first thing you see is the following. Suppose that I have some Lincoln diagram where, Lincoln diagram of say rank R, but it splits into R1 and R2 in such a way that you have R1 dots, whatever R1 dots here, this is R1 dots, and you have R2 dots. So this is some R2 dots. Okay. Now there are all these connections. You look at various connections. These things are connected somehow, or whatever complicated way you want to imagine. Yeah? And these things are also connected all sorts of ways, but there is no connection between this and this group. Which means that all this, if you take a dot here and a dot there, then the corresponding Aij, suppose this is the I and this is the j, so that Aij is equal to 0. That's what it means, right? When there is no, when Aij is equal to 0, you don't put any line. That means any of these roots, any of these simple roots here will have, when you look at the corresponding Aij with one of these, so one index is here and one index is there, is all 0. But then we saw that if that happens, then that means if I take, say, ith guy here and say j guy here, this I is arbitrary here and j is arbitrary here, then we have already seen that x alpha I, x alpha j commute. Right? The reason was, again, that was because that Aij or Nij, whatever, this is giving you information about the ith string passing through alpha I string passing through alpha j and vice versa for the AJI and Aij. But since these are simple roots, for them the p was always 0, right? So when you say the q is also 0, and when you say Aij is 0, that means the q is also 0, right? So the string length was the string alpha I string through alpha j string was 0 size, but that means that the commutator vanishes. Because if the commutator, this commutator would have been x alpha I plus alpha j, but we are saying that this simply doesn't exist. Alpha I plus alpha j is not a root, so therefore this is 0. This is 0. So that means these two sets, they commute completely with each other. So therefore, then this is not a simple algebra; it's a semi-simple algebra, right? Semi-simple algebra, remember, was a direct sum of simple algebras. Okay. So if you find in your diagram some two disconnected sets, subsets, right? That means you are dealing with not a simple algebra. Okay, it's a direct sum of simple algebra, which means some semi-simple algebra. So that, okay, one can, of course. So our aim was to study simple algebra, because if you know simple algebra, then you can construct any semi-simple algebra by just taking copies of them, add them up, direct sum. So that's all. So if you are talking about simple algebras, then the system, all these things should be connected. Then you should not be able to split it into two disconnected sets. That's the first thing. So for so this would not be simple. If this happens, then this is not a simple algebra. Because I mean, by definition of simple algebra was what? That it has no proper invariant subalgebra. No. But if you look at this algebra, commutator of this with that is 0 always, right? So this is a subalgebra, that's a subalgebra, and both are invariant subalgebras. Okay. So therefore, it is not simple algebra. So if we are focusing on simple algebras, we will just discard all such diagrams. So we will only consider those diagrams which are all connected, where you cannot separate them. Okay. Now there are several things. I mean, so we have these diagrams, but I mean, now one can ask the following question. I mean, can I just construct any? I just connect randomly, various points. So I've got R points, and I just randomly start connecting with one line, 2 lines, 3 lines, or 0 lines, and various points. Is it? Question you can ask: Is it a well-defined? I mean, is it consistent with all the things that we know? Is it possible even geometrically to do something? Basically, the question boils down to: can I find a basis? Remember, simple roots are a basis for the root space, right? So, can I find this R simple roots which has all these properties? All these lines tell you what are the dot products and all these things. All this information is contained here. So, can I draw it even in some R-dimensional Euclidean space? Because remember, here the metric is positive definite. We have already gone to the HR, the real part, right? In one of the previous chapters, we said that there's a positive definite metric. No? So we are working with that positive definite metric space. So there, the question is simply: is it possible to have this linearly independent vectors which satisfy those conditions that you are asking? And it turns out it is not. I mean, it's very, very restrictive. I'll just give you some examples. This is not included in the notes. All that this discussion now that I'm going to make is not included in the notes. But I mean, there are several conditions, but I will just go through one or two just to indicate to you that it is not so. It's not that you can just randomly draw any lines that you want. Huh? There are some conditions just coming from purely geometry, pure geometry, r-dimensional Euclidean geometry, and the demand that alpha i's form in linearly independent basis. That's it. To take an example, let's suppose I take just 3 points, r equal to 3. So take r equal to 3. And I just join all these three like that. Yeah? So we have alpha 1, alpha 2, alpha 3, and I just join this. Okay. Now, so that means one line is 1. So that means A1, 2 equal to A2, 3 equal to A3, 1 equal to minus 1. So the dot products. So this is I think so. Lengths are all equal. Lengths of all these guys are equal, and the angle is 120 degrees, right? Because it's all minus 1, minus 1. So the 2 alpha I alpha j divided by alpha I alpha j alpha I was equal to minus 1. So the angle and the lengths are all equal. So angle is 120 degrees. Like this we discussed before, right? So this 120 degrees. Now let's try to draw it. So I draw alpha 1, let's say here, and then alpha 2, 120 degrees. Okay. Alpha 2 here. Now I want to draw an alpha 3, which makes 120 degrees with alpha 1. You see alpha 3 with alpha 1, 120 degrees. Alpha 3 with alpha 2, also 120 degrees. But that the only way you can draw is if alpha 3 is in the same plane. In the same plane. So that this is 120, 120, and 120. This alpha 3 is restricted to this plane. If you try to pull this alpha 3 up out of the blackboard, I mean keep that point fixed, but take this and start moving up. Okay. Then the angle that this line will subtend with that and the one which subtends with that will become less than 120. Okay. You can easily convince yourself that is the case. So since I'm demanding that it's all 120, they are all forced to be in the same plane. But then they are not linearly independent. Because then you see alpha 3 is equal to alpha 1 minus of alpha 1 plus alpha 2. So in this case, alpha 1 plus alpha 2 plus alpha 3 is 0. Because you just add these 3 vectors, you get 0. Which you could have also seen directly from the definition. Let's look at alpha 1 plus alpha 2 plus alpha 3 square. Square dot product. Huh? So this will become alpha 1 square plus alpha 2 square plus alpha 3 square plus 2 alpha 1 alpha dot alpha 2 plus 2 alpha 1 dot alpha 3 plus 2 alpha 2 dot alpha 3. I'm just using a shorthand notation rather than putting that like this. Okay, let me put it like that. So this is really length square. But these are all 2, 2, 2. So length square are all, say we have normalized all this length square to 2, 2, 2. Or it doesn't matter. Let me just take out alpha 1 square. Take out alpha 1 square as common factor. Let's take out alpha 1 square. Alpha 1 square. Then this becomes 1 plus alpha 2 square or alpha 1 square, but the lengths are all equal. So it's 1 plus 1 plus 1. Right? And here we find plus 2 alpha 1 dot alpha 2 over alpha 1 square, which is the shorthand notation for alpha 1, plus 2 alpha 1 dot alpha 3 over alpha 1 square, plus 2 alpha 2 dot alpha 3 over alpha 1 square. But alpha 1 square is the same as alpha 2 square, so I can write it like that. Okay. And then these guys are all minus 1, minus 1, minus 1, minus 1 from that. So it cancels. So this whole thing is 0. So we are saying that this guy is actually 0 length. So since the metric is positive definite, that just means that this vector itself is 0, which we saw geometrically, right? All the 3 were in the same plane. So So therefore, this diagram is not possible. You know, it's not possible because simply geometry does not allow you to have 3 linearly independent vectors satisfying this property. So this is not there. Another example I give you again. Let's take three dots again. Three dots again, but I do the following way. I take 1 line here and 3 lines there. Okay. So that means angle between these two is 120. Angle between these two is, how much is it? 150, right? 3 lines is 150. We saw that in the table for 14.1. 5 by 6, which is 150 degrees. So that's 150 degrees. And since there is no, this is not connected, that means, by the way, the fact that this is not there, you can easily show that if these are for single lines, right? If I had double line here and single line, that is even impossible for people. Not even in a plane you can draw, because this will be 120 degrees, this will be 120, and that will be 135. There's no way you can draw it. This is simply not possible. Or if you put 3 lines here, this becomes even worse. If you increase the number of lines, the angle increases, right? Because single line means 120 degrees. Double line means 135 degrees. And triple line means 150 degrees. Okay. So if you increase the number of lines, it becomes even worse and worse. So a closed cycle is simply not allowed. And by the way, this I did it for 3, but you can do it for arbitrary numbers. Suppose I have some arbitrary number. Then again, you will see that if I take the sum of all these, okay, that is a 0. It's not easy to draw it in there now, but you can just take the sum over alpha I, alpha 1, whatever. Say there are n guys here, n guys here. So alpha I going from 1 to n. Then you can show that this square is 0. So the closed loops are simply not allowed. So it should be open. I mean, chain, rather. Chain, it could, I mean, there could be no closure. It can be chains, various chains, and there could be branches. But there will be no closed loop. That's it. Okay, now let's look at here. So since this is not connected, that means the angle between these is 90 degrees. Perpendicular. Dot product is 0. So it's perpendicular. Okay, so now again, you see, if you draw this, so let's say this is alpha 1, alpha 2, alpha 3. Okay, I don't even care about, for this argument, you don't even need to worry about the lengths, because one of them is bigger, longer, so it doesn't matter. It's just the angles which matters here. So I draw, say this is 150. And then I draw, so this is 90. I draw here. Then that's it. This is that correct? Yeah, this is 120. You add that up, it's 360 degrees. So once again, all the 3 are in the same plane. So they cannot be linearly independent. So this is not allowed. And similarly, you cannot show for this also, this diagram. You cannot put here. Also, it's not possible. Because this means this is 135, and angle between here is 90. So again, you add that up, it's 360. So again, these three points are living in the same plane. So it's not linearly independent. I mean, in such cases, if you try to prove it this way, it's not going to be alpha 1 plus alpha 2 plus alpha 3, because the lengths are different, right? So there could be some numbers here. Okay. There could be some not necessarily equal to 1. And then if you can find these numbers in such a way the square is equal to 0. Which just follows from the fact that they're at the same plane. So it has to be that. this vector plus this vector must be some linear combination of that vector, with not necessarily integer coefficients. Doesn't matter. That's not the important point. Important point is it's a linearly independent. So all these diagrams are not possible. So this is not possible. This is not possible, and this is not possible. That from this we can. Let me just try to tell you a few more examples. But, okay. For example, I have tried to. Yeah. What about the branch? If I take the branches, let's say this branch we said is a lot. We could think of a branch like this. But if you put another one here, so this is the point from where four lines are coming out. This is again not allowed, and you can try to do this. I'm just leaving this as some exercise. So here are all single lines. So the lengths are all equal, angles are 120 degrees. The angle between this and that 120, this and that's 150, this and that, and between these two, of course, 90 degrees because there is no line. So you can now try to prove. So let's call it 1, 2, 3, 4, and 5. Okay. You should be able to, if I have not made a mistake, I think you should be able to prove that alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 minus 2 alpha 5 squared is 0. I'm not 100% sure about this number, but I think so. Just try it out. Or if this is not the number, find what is the number. What is the correct number, which makes this 0. There is a solution to that. Okay. So that, again, this will tell you that since this is 0, that means these are not linearly independent. No? So this diagram is also not possible. So again, not possible. Then further, you can also show that this diagram is not possible. And yeah, I mean, at least I have not checked it for both. I mean, I have not found the solution for both. I didn't look for it actually. Because now I have to look at the arrow here. If I put the arrow here, it means this is longer than that. Okay. Then it seems again, if you take alpha, call it alpha 1, alpha 2, alpha 3, alpha 4, then it seems to me that alpha 1 plus alpha 2 plus alpha 3 plus 2 alpha 4, this square is 0. And again, I think also for, if you change the arrow, then I'm finding at least alpha 1 plus alpha 2 plus 2 alpha 4 plus 2 alpha 3. Okay. But anyway, I mean, maybe these numbers are not correct, but you can find out. You can just, when you look at, start taking this, open it up, you'll have alpha 1 square plus alpha 2 square plus alpha 4 square, alpha 3 square, and the dot products between the pairs. No? But this information you have from these lines. From these lines, you know the information. And this arrow tells you which length is bigger. No? So this one is for that, and this one is for this. So just try that, and you will see that none of this is possible. Now imagine there is a big diagram. But you see, even though I have here looked at only the 3 diagrams, you see this computation didn't care about all the other points. I mean, maybe there is alpha 4 sitting here, okay, which may be connected to that. Maybe alpha 5 is connected to that. Whatever. The rest of the things are not important for this discussion, because what we proved is that already this little part is inconsistent. If you put some other things from each of these points, you could start connecting to whatever other points. No, that doesn't matter. That's not going to change this discussion, because we're just focusing on this part, and this part is governed entirely by the A12, A22, and A23 and A31. No, that information is already here. So what I'm saying is that the fact that these are not possible, it means that it's not going to be possible even in a big diagram where some small part of the diagram happens to be this. One of these is not allowed. Okay. So that means very few diagrams, very few types of diagrams are possible. And I will just tell you the list. There's one more thing, which one more class of diagrams do not exist, and that let me show you. Incidentally, also there is a way to argue. I'm not going to argue that here. Just like this diagram here, right? I could have considered a diagram like this. Okay. This diagram really, what you can see, there's a rule which you can derive without much difficulty, that if I have a chain of single line chain, and then maybe these are connected to other things, other stuff here, other stuff, various dots and so on is connected. But you can actually shrink them. You can shrink them. So it says alpha, beta, gamma. You can shrink all of them to just one point, where this one point is connected to all the remaining guys. Or say remove just one point here, and say beta, gamma. And so you can shrink it if it is single line. So that means even such a diagram is not possible, because I could shrink it and then I could get things like that. I could shrink all of that, remove step by step. I remove this point, and then then you can. So upshot is, so what this means is that you cannot have any diagram with two double lines. There will be no diagram which has two double lines. So if double line appears, it's going to be only one double, nothing else. And the same thing, this discussion, again, you can generalize it by putting in various dots in between, various single lines in between. And you can show that, you can say that means, what this means is that if the double line exists in your diagram, then there cannot be any branch. Because this is telling you there is a double line and a branching. No? Branch means this one point is connected to 3 points rather than just 2 points. Okay. So there's not even branch. So only possibilities then are this type. So far from this discussion, the only possibilities are you can have just single lines. There's no problem with that. I mean, as many numbers you want to put. So this series is called AN. AN series are the ones where the dots, there are n dots here. This means n dots. Okay, but they're all connected in a line with single lines. That's one. Then there is a BN series, which is this here, where just the last one is going like that here. So the double line here, the last one. So n. So this is, say, the 1, 2, n. All these other guys are just connected by single lines. And now here there are two possibilities, because now I have to specify which one is longer and which one is shorter. So if this is shorter, then this is called BN series. If you reverse the arrow, same diagram, except that you reverse the arrow. So that means this is longer. Then this is what is called CN series. N is always the number of points. And then there is a series, the branch series, which is what is called BN series. And that series is like this. So there's a branch at the first, let's say I call this 1, alpha 1, and then alpha 2, up to alpha n minus 2. And this one is, say, alpha n minus 1 and alpha n. This is called BN series. And finally, so these are the infinite series, which means that n could be arbitrarily as large as you wish. There's no limit on the n can be. But then there are some what is called exceptional series, exceptional ones, which are only finite. I mean, they're not. They don't have this n parameter. Exceptional. One of them is G2, 3 lines. The 3 line, since I cannot put any even a single line. That means 3 line exists with only 2 points. You cannot have anything more, right? Because any other point you put, since we are talking about a simple algebra, it has got to be connected somehow to this, right? To the system. Otherwise, you're not talking about a simple algebra. No? So that is not allowed. So this is the only Lie algebra which has 3 lines, and this is called G2. G2. I mean, the group is called G2. This is a Lie algebra. Right? We're talking about the Lie algebra. Then you have a with the 2 lines. It turns out that there is a 2 line. Okay, so the ends, one end. You know, you see this series, and this series. The 2 lines are appearing at the end, the one end. So you don't have a situation where these 2 points which are sharing these 2 lines, you have a line coming out there and a line coming out there. That's not it. This is in the end. But there is one exception, which is this one. This one is allowed, and this is called F4. 4 because the rank is 4, right? 4 points. G2, 2 means that there are 2. Rank is 2. And finally, there are 3. So this is the only other thing which contains 2 lines, apart from the ones which are sitting at the end. This is the only one, because again you can prove using this similar techniques that if you have a line, if you have something like this, this is again not allowed. This is not allowed. And, do I have this? I don't have it here. No, I don't have it here. But I mean, I don't have it. But again, you can try this. Huh? You can try this. You should be able to find some combinations of these roots, which has length square 0. You know, with either choice, this way or that way, you should be able to find. So this is not allowed. So the only thing which is allowed is here, this one. And finally, there are some things which have which are all single lines, but with branches. So the one thing we already saw, the branch, so these are the DN, but this has a peculiarity. You see, if you look at the branch points, from one end you have a large chain, but the other 2 are only single. I mean, they're just there's not a chain like that. No? But there are exceptions. One is called the E6, which is going like this here. 1, 2, 3, 4, 5, and 6. This is not of that type, you see, because if you look at the branch point from there, there's one side you have 2, one side is 2 and 1. Here it is 1, 1, and here it could be arbitrary. So this is not, this is different. E7, where you just take this thing, add one more point. And finally, E8. This is it. So one more point here. 1, 2, 3, 4, 5, 8. This is what is left over. These are what we call classical algebras. These are the matrix algebras that we know. Okay, I will tell you. I mean, I will go through the what's. On Monday, I will go through the connection between that. These are the SUN plus 1 or SLN plus 1. SL plus 1. This is the same as SUN plus 1. I mean, since we have complexified, this is really SLN plus 1. But when you go to you can go to the real basis, then it becomes SUN plus 1. N plus 1, the rank is M, no? So that's why it's N plus 1. These ones are SO 2N plus 1. These ones are symplectic, SPN. And these ones are SO2N. So there is a distinction between SO even and SO odd. There's a big difference. Lie algebra, from the point of Lie algebra, is very different. It's very different. But okay, these were the kind of let's say these were not known before this classification. After when people started classifying and going through this general structure theory of the Lie algebra, then they found that there are these additional ones. And they played a lot of role. Okay, F4 I don't know so much, but G2, as I said, plays a role in what is called M theory, and also string theory. And these guys play an important role in string theory. Okay. They all play an important role. So there are a few things that's to. I mean, for example, you could try to prove if you take. I mean, so you see that when you have branch, so the three things are coming out. One of them must be always of length 1, right? You see, this is length 1. Also here, length 1. So one of them has to be length 1. Then other guys can be length 2 or 3. So two here, 2 here, 2 here, 3, 2, 4. But after that, it doesn't go. On the other hand, if 2 of them are length 1 each, then the other can go anywhere, as far as you wish. But if one of them is length 2, one of them is length 1, and if other guy is length 2, then this side can only be 2, 3, or 4. So there are this, again, you disprove by, I mean, you show that it's not possible by just looking at this diagram. For example, this, you can show that this vanishes. I mean, this is not possible just by taking a linear combination of this with the 1, 2, 3, 2, 1, 2, 1, which means 1 times this root plus 2 times this root plus 3 times this root, and take the square. You show that you can show that it is 0. Similarly, if you take something like this, 1, 2, 3. So now what we are doing is this is length 3, right? Now let's take length 1 here, length 2. I mean length 2 here, length 2. And if you take one of them length 2 and this 3, once again you can show this vanishes by taking 1, 2, 3, 4, 3, 2, 1, 2. So combinations with this, and you can show that, etc. So I mean, you can prove after going through all this, you find that the only possible geometrically, the only possible diagrams that you can have, which is connected, is this. That's it. And these are the algebras. Now I think what else I can do here? So let me just let me do the following. What I will do now is you just construct all the rank 2 algebras. Then on Monday, hopefully you have gone through that chapter 13, right? Chapter 13, which basically goes through the construct the roots for the SUN, SO2n, SO2n plus 1, SPN. For all of them, it constructs the roots. And so if you have gone through that, then it will be much easier to show that this is the corresponding thinking diagrams, which I will do on Monday. So we'll postpone that. Instead of that, I will try to construct all the rank 2 algebras. And just one small comment. In SU3 case, remember, in SU3 case, which is a special case of AN, so A2 is SU3. A2 was simply the 2. This is SU3. 2 lines. We said that, so this is just alpha 1 and alpha 2. We said that any representation, any irreducible representation can be constructed by just starting from the highest weight. No? Highest weight, okay, now here you have 2 simple roots. So highest weight is given by specifying what spin represents, because each of them defines to you an SU2 subalgebra, right? So you can talk about the spin with respect to this SU2 and that SU2. No? So basically, it was any representation was specified by specifying how the highest weight in which spin representation of this and in which spin representation of that was there, right? We actually multiplied by a factor of 2 to make all these things integer. No? So in that language, we had just n1 and n2, two non-negative integers. You specify that, and that defines to you uniquely a irreducible representation, right? So just any non-negative integers. So the same thing happens here. In all of this diagram, everywhere, you just put randomly whatever integers you want to put. No? At each dot, you put some integers. That what does it mean? That means that because each of these roots defines you an SU2, it just tells you the highest weight is transforming under which spin representations of each SU2. No? So you just specify the numbers, and 1 and 2. Okay, let me count. Start. No, n is already here. Okay, n1 and 2 and 3, etc. Until n. No? You just specify this n integers. No, maybe I shouldn't put here n. Called k1. Because n I'm using for the rank. So just specify these numbers. So this would mean it is spin k1 by 2, spin k2 by 2, spin k3 by 2 representations with respect to these respective SU2s. And then from there you can construct. Of course, it's not as easy as to doing an SU3, because SU3 you're only plane, you're moving in the plane. Now if you go to SU4, you have to move in 3 dimensions. So it becomes very difficult, but in principle, it is labeled by these numbers. I mean, in the kata, this Young diagram, this would just correspond to taking a box with the kn in the lowest box, kn plus kn minus 1 in the next one, and so on. That would be the Young tableau representation of this. And so on. So again, we will not go through that because I mean, to construct this will be hard. But in any case, they are labeled by this. So what I will do now here is just to look at all the rank 2 algebras. So the rank 2, we have only this possibility. There are just 2 possibilities here, right? I have this possibility here, or I have this possibility. Right? It doesn't matter. You see, even if you look at this Bn or Cn, if you have only 2 points, so that means none of these things exist. Then what's the difference between these 2? It is just if you relabel the 2 roots, this diagram is the same diagram there, right? So that's why A2 is the same as B2. Sorry, B2 is the same as C2. B2 is the same as C2. So there's no distinction. You just exchange the 2 roots. That's all. Huh? It's what you call labeling of the root, nothing more. So that is the reason why, I mean, we also saw before that this was SO5. I mean, SO2n plus 1. So SO5. And that is SP2. Sorry, SP2. These 2 are the same. At the level of Lie algebra, not at the level of group, at the level of Lie algebra. This is all discussion about the Lie algebra, not about the group. So at the level of infinitesimal generators. So at the level of Lie algebra, it's exactly the same. That's but the moment you have one, once you go to n equal to 3 and n equal to 4, etc., then these 2 diagrams are different. Because this would mean, this is a longer route than that. So therefore, this is equal to that length, because there's only one line. The length of this should be equal to the length of that. But this means that this and this both have length greater than that. No? Whereas here, if you look at this situation, here the length, this one is longer. So both of these guys are shorter than that. So now B3 is different from C3. They are not the same. It's just a peculiarity of B2 and C2. The rest of it is all different. Okay. So this is a possibility, and of course, and finally for just n equal to 2, these are the 3 possibilities, right? Nothing else. Of course, the one which is not simple is this one, no connection at all. Okay, but that just means a single point is just a SU2. So this is one SU2 and another SU2. It's a direct sum of 2 SU2s. Okay, that's not very interesting. Actually, this is also this is SU2, direct sum SU2, which is the same as SO4. Okay, again, at the level of Lie algebra, it's the same. I mean, we didn't do it. Huh?
In complex number.
In
Complex number or
SO4. So this SO4 real. I mean, SO4 real. So this is dimension 4 times 3 by 2 real. Huh? So that is 6 dimensional. And SU2 3 dimension and 3 dimension. real three-dimensional. Real SU2 is Hermitian, 2 by 2 Hermitian matrices. So that will be 3 real plus 3 real, so 6. So that's the same. But it's not just the counting. Counting is one thing. Of course, counting has to match, otherwise it cannot be. But algebra, the point is that algebra is the same. This is much more non-trivial. So forth. But
this one is in complex.
Yes.
SO2N.
SO2N is, yeah, I mean, in doing all this, we use the complexification. But after having done that, we can just go back and go to the reals. Yeah. I mean, usually when one says AN, BN, CN, etc., one is really thinking in terms of complex algebras. But you know, you can just restrict to the some subspace real part. Then here you will get SU n plus 1, whereas here you will get SU2 n plus 1. So in the same way that we described, I mean, you have to, like already for SU2, I mean, from the, you know, in SU2 already, we had the what we call x plus minus was x1 plus ix2. No? X1 and x2 were the elements of SU2, but then we complexify to find eigenstates. But then you can reconstruct x1 in terms of x1 and x2 in terms of x plus and x minus. And then after having done that, then you only allow real coefficients. Okay, so I want to do, so this is already, this is trivial. This we did, SU3. Now what about this guy? So let's see if we can try to do that. So here is alpha 1 and alpha 2. And finally, this alpha 1. Actually, let me focus on this because that this will turn out to be SO5. SO5. This will turn out to be SO5. But let's look at this. This is more completely new. I mean, it's none of them. It's not a matrix. It's not, doesn't come from the matrix groups. So let's see this. This is interesting because so we can do it the following way. Maybe I should introduce some notation, some kind of a thing. You can define a level. So in general, what will happen? I mean, we'll start. So okay, let me draw it here. Say this is alpha 1, and you have alpha 2, whose the angle is, remember, is 150 because this is, so angle is 150 degrees. So I'm just trying to draw it in a way that you don't have to do it, but okay, 150 degrees. So which means this is 30 degrees. And moreover, this length of this guy is, okay, I choose this to be this one here. So length of this is √3 times that. So this is alpha 1. So I don't know. So I should really go up a bit or make this smaller a bit. Okay, √3. Something like that. So this is √3. So this length, alpha 2 length, is √3. Alpha 2, the length of alpha 2 is equal to √3 times alpha 1. Because alpha 2 square was 3 times alpha 1 square. So, okay. And furthermore, this if I look at the two numbers, so if I look at the alpha 1 string through alpha 2, which was 2 alpha 1 dot alpha 2 divided by alpha 1 square, which was p minus q, but p is 0, we know. So this is minus 3, right? There are 3 lines. 3 lines means it's minus 3. Not very clear. Equal to minus 3. Whereas 2 alpha 1 dot alpha 2 over alpha 2 square, in other words, if I look at alpha 2 string through alpha 1, that's going to be minus 1, right? In fact, that is the reason why we concluded alpha 2 square is 3 times alpha 1 square. No? So, because this is 3 times that, so this will be 3 divided by 3, so it's minus 1. Okay, so this means, if I look at the alpha 1 string, it should be, this is the 3, so there should be, q must be equal to 3, right? So I should go, so something like this here. The picture is not very good. Then here, then here. Okay, so this is alpha 2 minus plus alpha 1, alpha 2 plus 2 alpha 1, and alpha 2 plus 3 alpha 1. Actually, the more systematic way of proceeding is just do level by level. You try this, no, you can introduce a notion of level. So if there is some root which comes out to be n alpha 1 plus say m alpha 2, then the level of this root is the same as n plus n. This is just a matter of definition. I just call this as level. So from this definition, the simple roots themselves are at level 1, right? Because one of them is 1, other is 0, no? For simple root. So simple roots are level 1. And then when you start adding simple roots to get other positive roots, you can associate a notion of level with the positive roots, right? So because any positive root, I can write it as linear, as a sums of alpha 1 and alpha 2 with some integer coefficients. So now you just add those integer coefficients, and that's a level. So from this language, this is level 1, level 2. So this is level 1, level 1. So these numbers I'm writing are levels, because this is 1 plus 1, whereas this is level 3, this is level 4. Okay, so let's systematically do level by level. Maybe do that. Okay, maybe there's some one theorem I think I forgot to prove, but I will go back to it later. So that is one. Now let's see. So I started with alpha 1 and alpha 2 roots. I know that this string from alpha 1 string will go all the way to alpha 2 plus plus 3 alpha 1. So in particular, so this at level 1. At level 2, so here is level. At level 2, we have alpha 1 plus alpha 2, right? That's it. Because also from this point of view, if I look at the alpha 2 string through alpha 1, this means this is a doublet. So it will just stop here, alpha 2 plus alpha 1. This minus 1 means it's a spin half, no? And this is spin 3 half. So that's why this is spin 3 half representation, 4-dimensional representation. This is spin half, so this will be a 2-dimensional representation. So it stops here. Anyway, so level 2 we have only this state. Now let's look at level 3. Level 3, I can start from level 2 and add alpha 1 or alpha 2, right? So there are a priori have two possibilities. I can put 2 alpha 1 plus alpha 2 or alpha 1 plus 2 alpha 2. Okay. Now we said alpha 1 plus 2 alpha 2 does not exist because that would be the alpha 2 string. No, that is not there. It stops here, right? I mean, this is q equal to 1. Q equal to 1. So it can only go alpha 2 plus alpha 1 plus alpha 2. It cannot be alpha 1 plus 2 alpha 2. So this is not there. So we have only this possibility. Then let's go to the level 4. Level 4, I can add to a level 3 guy, which is only this one, either alpha 1 or alpha 2, right? So I can take 3 alpha 1 plus alpha 2, or I can take 2 alpha 1 plus 2 alpha 2. Right? Is there some other possibility you can think of? Yeah, this is all, right? 3 alpha 1 plus alpha 2, 2 alpha 1 plus 2 alpha 2. So, so what is it? This is there. This is there. This we already see there. But this cannot be, right? Because after all, this guy, I can write it as 2 alpha 1 plus alpha 2. Now, alpha 1 plus alpha 2 is a root. And we know 2 times that cannot be a root. No? So this is not there. Okay. Now, let's go to the 5th level. Let me see if I'm doing it right. Or I release something. So the level 4 is just 3 alpha 1 plus alpha 2, correct? Yeah, so level 5, we have 2 possibilities again to start with. 4 alpha 1 plus alpha 2 or 3 alpha 1 plus 2 alpha 2. So 3 alpha 1 plus. So now if you look at this here, this is, if I start from alpha 2, then I should get a, if there's a 4, that means it's a chain which includes the 4, but that is not included because this value was 3. Q was 3. Q was 3. So alpha 2 plus 4 alpha 1 doesn't exist. This doesn't exist, right? Because this was a spin 3/2 representation. So this doesn't exist. What about 3 alpha 1 plus 2 alpha 2? This is perfectly possible because I can 3 alpha 1 plus 2 alpha 2. So it is somewhere coming here. So, but in order to do that, I have to check. One has to check the, so if you look at this alpha 2 plus 3 alpha 1, let's look at that. So we want to ask, if I start from here and I consider alpha 2 chain, do I have something? Do I get something? I mean, from that I can conclude, because this guy is not there. You see, the previous one is not there, you see, because previous one would be alpha 2 plus, no, that would be 3 alpha 1. You see, if you look at the alpha 2 chain, sorry, maybe I'm not. If I start from here and I look at the alpha 2 chain, okay, alpha 2 string. If I add an alpha 2, I'll get 2 alpha 2 plus 3 alpha 1. If I subtract an alpha 2, remember, is this one, right? So adding alpha 2 is taking you this way. Subtracting alpha 2 is going to go down. But if I subtract alpha 2, I'll get 3 alpha 1. But 3 alpha 1 was not a root because an integer alpha 1 is a root. So 3 times alpha 1 cannot be a root. So this doesn't exist, right? So that means it starts from here, right? So if I compute this dot product, I mean, call this guy as beta, something, call this beta. So we want to look at the alpha 2 string starting from beta. So we just want to compute 2 beta dot alpha 2 divided by alpha 2 square. We want to compute this, right? Because this is going to give me the corresponding p minus q. But I know p is 0 because this guy is not there. Right? If p was equal to 1, you should have this, but this is not a root. Okay. So I know p is 0. So then whatever I will calculate, it will immediately tell me what is q. Okay. So let's calculate that. Beta is we said alpha 2 plus 3 alpha 1, right? So this is the same as alpha 2 plus 3 alpha 1 dot alpha 2 divided by alpha 2 square. So this first term is 2 alpha 2 square divided by alpha 2 square, so that is 2. And the second one is 2 times, so this is 2 times 3, so this is the same as 3 times 2 alpha 1 alpha 2 divided by alpha 2 square. But that is minus 1, right? This was a minus 1. I mean, right? This is the longer, I mean, when it was alpha 1 square, this was 3. That is the reason why we have these 3 lines. But alpha 2 square is the bigger one, right? Alpha 2 is the bigger one. So its length square is 3 times the length square of alpha 1. So this is actually minus 1. So 2, so this 2, sorry, yeah, 2 plus this, right? So 2 minus 3, so it's minus 1. So this whole thing is minus 1. Is that, I mean, did you follow that? Maybe let me write it again quickly. So what I'm saying here is that, let's open this. So first term is 2 is coming from here, alpha 2 dot alpha 2 divided by alpha 2 square, which is 1. The second term is 2 times 3 alpha 1 dot alpha 2 over alpha 2 square. But this quantity, we already know from that this figure, and using the fact that alpha 2 is the bigger length, alpha 2 is like the square root of 3 times alpha 1. No? So this thing is simply minus 1. So the result is 2 minus 3, right, from here. So which is minus 1. That means Q is 1, since P is 0. Okay. So which means this is allowed. I mean, this has to exist. It's not just allowed, but it has to exist. Right? Because this is telling you this is a spin half representation with respect to this SU2 subalgebra, and you have that. And that's it. That's the 5th level. Now, if you go to the 6th level, so this exists. At the 6th level, I can either add alpha 1 here or alpha 2. So if I add alpha 1, I will get here 4 alpha 1 plus 2 alpha 2. And if I add alpha 2 here, I get 3 alpha 1 plus 3 alpha 2. But this is, you can take out a common factor 2. So 2 times 2 alpha 1 plus alpha 2, but that is a root. 2 alpha 1 plus alpha 2 is a root. So twice that cannot be a root. So this is not there. And here, if you could take out a common factor 3, so it's 3 times alpha 1 plus alpha 2. Alpha 1 plus alpha 2 is a root. So it cannot be. So that's it. It stops there. There's nothing more you can do. So what are the things here? There is this. So we have recovered all these 4 points, and we found another point here. Okay. Now let's try to just draw it just out of curiosity. So of course, for each of these root, I have also a negative root, right? So there is this here, this here, this here, and this here. So a negative root that corresponds here, this is a negative root. A negative root of that will be somewhere here. Negative root of that will be somewhere there. Negative root of that will be somewhere here. And this guy will be somewhere here. Here. And for this one is here. Okay. So that's the root diagram here. And of course, the origin. The origin, of course, the Cartan. That's the Cartan part here. 0. And this is again another beautiful picture. You just try to just trace the boundary. If you just trace the boundary, it's this picture here. As a star. Yeah. That's G2. Yeah, you can, yeah. You can see that this has an SU3 subalgebra, because if you look at just the outer points, you get, yeah, if you take any of this, if you take this root with that root, I'm going to get, I mean, take the commutator of this with that, I will get that, no? And so on. So you'll get, yeah, so there are SU3 subalgebras and so on here, but it's a whole thing is very complicated. These points, if you take these 6 points, outer hexagon, that will give you an SU3 subalgebra, and yeah. The inner one is not. If I look at the inner guy, you see this, that you cannot say it's an SU3 subalgebra. If you look at the inner hexagon, this hexagon, because if I take the commutator of this with that, if it was SU3, it should have been 0, right? But here it is not, because if I take the commutator, I'll get that. So the inner guy is not giving SU3, but outer guy is giving SU3. So that's the, yeah, G2 space. Okay, so let's do the following then. I mean, try to go through it, that chapter 13. Chapter 13, which, as I said, basically gives all the, constructs all the roots for the SO, for all these matrix algebras. I mean, the AN, DN, CN, DN, which means SONs, SO2n, SO2n plus 1, SPN, and SUNs. So construct all the roots. And then once you have gone through that, then we can try to see how this reproduces the Baking diagram. AN, BN, CN, and Baking diagrams. And then if I have some time, I will try to look at the spinor representations. Because that's rather important. I would just make one comment here, just to give you some idea of what's happening. So what happens is that, so if I look at the DN series, this is the DN series. So this is the SO2n. So, so here there is a bifurcation. I mean, there's a branch but each of length 1. And here it could be arbitrary. So if this is 1, so this is, say, this is n minus 1, alpha n minus 1, alpha n, then this will go up to alpha n minus 2. So 1 up to alpha minus 2. Now, I mentioned to you that, I mean, there is a kind of a symmetry here, right? You see, I could just exchange these two, keeping all of these guys fixed. There is symmetry here, right? That basically, what that boils down to is actually, okay, maybe I should mention. As I mentioned, that you can write down any representation just by specifying integers here, no? By specifying, just like for SU3, we said you can, for SU3, we said you just specify two numbers, n1 and n2. That defines to your representation, no? Irreducible representation. The same thing happens here also. But so what happens is that if you put here 1 and everything else is 0, 0, 0, everything else 0, then this gives you the vector representation of SO2n. Vector representation, of course, is a 2n, the defining representation, 2n column vector. So the 2n by 2n matrix. So this is just where, I mean, so it's a vector, and the vector is rotated by SO2n. So that's that. But if you put 0 everything, 0 here, and sorry, everything 0, except one of them 1, and other is 0. Everything is 0 except for one of these. Okay. Then that gives you a spinor representation. A spinor representation of SO2n. That is, if you want to put a fermion in a 2n dimensional space, that will be the representation in which fermions will transform. So this will be the spinor. And this one, so this is the spinor representation. One of them, that's up to you to decide. And other guy is called the spinor prime representation. So this is to do with the chirality. This spinor has one chirality, and other spinor has opposite chirality. Okay. You have looked at you've studied the chirality in the RQM. Yeah. So this is what happens. Now, on the other hand, if you look at the SO2n plus 1, that is a different structure altogether, right? It has a double line with the arrow in this way. Now here you see you don't have this thing, but this one anyway, in odd dimension there is no concept of chirality. If you have odd dimension, this is SO2n plus 1, this is SO2n plus 1, where n is the number of points here. The SO2n plus 1. In odd dimension, there is no concept of chirality. Chirality is a concept only in even dimensions. So in odd dimension, there's only one type of spinor. There's no question of chirality. But in any case, so this will tie in with so if I have time on Monday, I'll try to do the spinor implementations after finishing this one. After the chapter 13, which if you have done it already, that I don't have to spend time on that. Okay. All right, so I think I'll stop. Okay, there was one theorem which I didn't do. Yeah, this proposition 14.2. I didn't. Okay, maybe I will not do it now. There's I missed that proposition 14.2. 14.2. This I have not done it. I missed that, but if needed, we can discuss it on Monday. This proposition is basically just formalizing this procedure that we started with, going level by level, and it just tries to formalize it. And it basically, the statement is that if at some level, like here, for example, I stopped at level 6, level 6 I stopped because there was nothing there. So then one can ask, why didn't I go to level 7? Level 7, there could be, say, 4 alpha 1 plus 3 alpha 2, and so on and so forth, right? Why is it not there? But what that proposition shows is that if at a certain level there is no state, then at the next level there cannot be any state. in that case. Which is again, I mean, not too surprising, right? Because after all, how can, I mean, these are SU2 which are moving you around. Suddenly at some place there is nothing, how can there be the next one? No? It's kind of pretty obvious. So I think tomorrow the tutorial, and then maybe you have, do you know when is exam, RQL exam? It is going to be next week, but I don't know which day. I think most likely it will be towards the end of the next week, you know, so that you have time for the RQL. Probably Thursday or Friday. So if you you can arrange with the ARIDA tomorrow, you know, whether you want to have another tutorial next week or you just want to prepare for the RQL. No? In any case, what we can do is that Monday we'll meet again anyway, but then the week after we try to meet one day. You can arrange also with Aida if she is free the first week of November. No? Maybe she can arrange to have a tutorial. But I can also meet you, meaning that after you have gone through, and you may have many questions at that time. No? So maybe we can have a session where we just ask questions. Huh? So I will try to do that. Friday is exam, so you think Thursday would be good enough? I mean, so you'll have enough time to.
I think a little before Thursday, maybe
Yeah.
Wednesday.
Sorry, repeat that again?
Like maybe Wednesday would be suitable.
Wednesday. Okay, the only thing is that I might be out of town. I'm not 100% sure. Okay, I will let you know. Yeah? So if Wednesday is not possible, should we try Thursday?
Yes.
Okay. So I will try for Wednesday, but I'm not sure. I might be out of town. So see you on Monday.